Okay, right. So, so this is something that we have, right? That for all vertices, this is the case, all graphs. So what does it mean for the case of the planar graph? For the case of the planar graph, therefore, summation of di I in the vertex set is less than 2 times this quantity, right? Which is 2 times 3 into v minus 6, which is 6 times v minus 12. So that means sum of the degree of all the vertices is less than 6 times the total number of vertices minus 12. So from this, what can we say? So from this, we can say that there exists a vertex, okay, such that the degree of that, say, vertex v, the degree of v is less than or is actually strictly less than 6. Are all of you fine with it? Are all of you fine with it?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So this is another property you can think of a planar graph, that you always have a vertex that has degree strictly less than 6. Okay, now note that this is a connected graph. Okay, this is also something that we had kind of talked about. If G is a connected planar graph. Now, using this concept, I can now start, okay, I can start coloring the graphs. Okay, I can start coloring the graph. Okay, why? Or how can I start coloring the graph? So we start with, so here is the G, okay. I start with the vertex phi, which has the smallest degree. Now it has degree certainly less than 6, that means it has degree at most 5. Now I color this, so at any point of time, this is what I will do. I will find a vertex with a minimum degree that is not colored, and I look at its neighbors. Okay, I look at its neighbors. Now the neighbors might have got some colors. Okay, when the neighbors got some colors, at most 5 colors have been used by the neighbors. So the 6th color, so I have say color number C1, C2. Maybe this is not a C2, C1, C2 is not a very good idea. Say I color it as red, blue, yellow, green, white, and orange.
Sir, but you said we are starting to color it. So neighbors will
Yes.
not have any color now.
At this point, none of the neighbors have any colors, right? So I can color the vertex anything I want. I don't care at this point, right? I just want to color that vertex with a color which is different from the rest of the neighbors. If the neighbors are not colored, then no problem. I just don't, so we can think of, I can color it in anything. So say I start by coloring this one arbitrarily with a red color. Maybe I should use some. Okay, so I arbitrarily color this one red. Correct. So now in the remaining graph, okay, so in the remaining graph, the graph can have something. Maybe I should draw some graph like this. Okay, so some graph like this is there. Now in the remaining color, I take another vertex. Note that if I remove this vertex, okay, if I remove this vertex, right? So G minus E, sorry, not E, G minus V. What is this graph? This graph is still planar because removing a vertex still remains, it makes it planar, right? Fine.
Yes, sir.
Sorry, I made mistake. I made a complete different mistake here. Okay. No. Sorry, whatever I told is wrong. I just was saying something. So sorry, I don't color this graph vertex. I start with this vertex. Maybe I should not color this vertex. Okay, I take this vertex. Now this vertex have five neighbors, right? So what I do is that I will remove this vertex. I'll just remove this vertex. What happens if I remove this vertex? Maybe I should kind of for now erase this vertex. Okay, I remove this vertex. So there are vertices over here, but note that this graph there is a vertex over here. Okay, and maybe there are edges like this also. That is fine. But then, I mean, what I want to say is that there is a vertex like this. This is the vertex V. But what happens if I remove this vertex from this graph? I get a new graph of which is planar, right? So this is planar. And this one is a graph with one vertex less. So in some sense, I can say that, okay, fine. You have asked me to color the whole graph. I have picked up this vertex V, removed that vertex V, and I have produced a smaller graph. Now I've told you that, okay, now go and color this one, this smaller graph. Okay, so by induction hypothesis, this smaller graph has a coloring, has some coloring, and I don't know what coloring is it, some coloring. So this, maybe this is red, maybe this one is orange, maybe this one is blue, maybe this one is green, right? Maybe something else, maybe this one is yellow, right? And so on and so forth. But now you have come back with a coloring of the remaining graph. I mean, I know that the remaining graph, whole graph has been colored, right? So for example, this one is red, this one is also red, some kind of colorings of that kind. This was green, this one is green. This one is yellow, this is yellow, this is yellow, this is yellow, and so on. Maybe this one is white in color. Okay. Now at this point, you have given me this coloring, a valid coloring of G minus V. Now I put back this color. Now I put back this vertex. Now see that every other vertex have been colored properly. So the thing that has not been colored is only the vertex V. And the vertex V has how many colored, how many neighbors? Exactly 5 neighbors, right? And these 5 neighbors can have used at most 5 colors. So there must be at least one color, so which in this case is the white color, that is not used by the neighbors. So I use it to color the vertex V using the white color. Okay, and this is basically how we will be able to color the whole graph. This is basically induction. Take the big graph, find the vertex with the minimum degree. Now there must be a vertex of degree less than or equal to 5. Take that vertex out. And once you take that vertex out, then the remaining color or remaining graph has one vertex less, and you use induction hypothesis to color that smaller graph, and then color the last vertex, which has degree at most 5, using the sixth color that is not used by its neighbors. Is this clear? Hello? Just
Yes.
1 second, I have to take this. Hello? Hello. Yeah, hello, sorry. So is it clear? Any doubts about this thing? Questions?
Sir, could you tell us why the degree is less than 6 once again?
Yeah.
Minimum degree?
So, yeah, so minimum degree is less than 6 because, so you are familiar with this concept that sum of the degrees is equals to 2 times the number of edges?
Yes, sir.
Yeah. So, and in the case of the planar graph, this is something that we did last class, right? That number of edges is less than 3 times the number of vertices minus 6.
Yes, sir.
Right? So using these two statements, I can get some statement like this, that summation of the TI, all the degrees, is less than 2 times this 3 times 6V minus 6,
Yeah.
or which means that summation of the degrees is less than or equal to 6V minus 12.
Yes, sir. I understood till here.
Right? Okay. Now, okay. So there's two ways of seeing it. One is this is called the averaging argument. So basically, thing is that what happens. So what is the worst case can happen? That every vertex have degree more than 6. Right?
Yes, sir.
If every vertex have degree more than or equal to 6, then what is the summation of the degree?
6 into V.
6 into V. But is 6 into V less than 6V minus 12?
No. Okay, sir. It is clear.
Okay. So basically, I mean, if the summation is something, then there will be one which is more than the average or less than the average. Here the average is less than 6.
Okay, sir. I understood.
Okay. Is this fine? Is this one? Any doubts about this this kind of this thing about how to color up?
Yes, sir.
Okay. Good. So now let us crank up our problem a little bit more. Let us see if I can prove that a planar graph can be colored with 5 colors. So I claim this statement. Okay. A planar graph Oh, by the way, there is a small catch here that I have not told you guys here. That is something that I have not told, and I want you guys to go back and think about it. The way in which I kind of told that, okay, take this G and G minus V and all those things, but who told us that what if G minus V is not connected? See, everything that was told was for the connected graphs, right? What happens if G minus V is not connected? Then what do you do? Say, think of this graph is something like this, okay? It's a planar graph. Maybe this is the V that I choose. And when I am going to remove this V, I will get two disconnected components, this one and this one. What do you do now? How do you prove it?
So the components themselves will be connected.
Yeah, go ahead. The components themselves will be
Connected.
yes. So individual components will be connected, right? And individual component will be planar. So inside individual components, then you have to go within a component and then kind of do it. So the induction hypothesis is not just, I mean, you colored G minus V, but this G minus V might be a disconnected graph also. Okay. And in fact, I mean, this statement that we told that there exists a vertex such that this statement is also true for it is true for any connected components, and therefore it is true for any planar graph. Okay. Okay, so now let's go for this one. Can we prove that a planar graph can be colored using 5 colors? See, it is almost same as the case of the, I mean, for the 6 color stuff. Okay, we will do an induction. Okay, we will do induction. And the idea is that if I can find, I mean, if there exists a vertex with 4 degree, then done, right? If I can find a vertex of degree 4, then I can go to a smaller graph of more degree, a smaller graph. And you give me any vertex. So basically, if there's a vertex V, then done meaning consider G minus V. G minus V is a graph with 1 vertex less. Give me a coloring of that using 5 colors. But since we just have 4 neighbors, so I can color V using the 5th color. Right? Any question? No question? Excellent. But there is also a possibility that I don't find a thing, right? So the minimum degree vertex is minimum degree vertex has degree 5. Now that is possible, right? So there is a vertex, or I cannot do much about it. There is this graph, and this is the best that I can find out. and this graph has degree 5. Okay. Now, of course, if I remove G minus V, I can get a coloring using 5 colors that the induction hypothesis says. Okay. And in that case, so maybe again I had red, blue, green, yellow, and white, right? So say this one has been colored red. This one has also been colored red. This one, oh, there's an orange also. Or maybe white is not a very good idea. And the orange.
Sir, I have a question.
Yeah.
Sir, is it possible that we
Go
will
ahead.
not find a vertex, like minimum degree will be 5, because then won't K5 be a
Yes,
subgraph
it
of
is
that?
possible. No. No, actually not. You can find out vertices with minimum degree 5. Yeah, you can have vertices of minimum degree 5, and the K5 will not be a subgroup of that. Because I mean, it is not necessarily the same set of vertices, right? It will be kind of very weirdly connected and all. But you are in a kind of a right direction, so you can actually think about this direction later on. I mean, it's not exactly stay right, but something similar to whatever you told is kind of correct, and that is something that is used for the 4 coloring theorem. Or you will see it here also. So, for example, here say somehow luckily I have got this coloring. Okay, I don't know what are the other colorings are, but the neighbors of V have colors 2 red, 1 yellow, 1 orange, and 1 blue. Now, can I color the vertex V using some color? One of the 5 colors. Hello.
The green, sir.
Green. So I can color. So how could I color it with green? And still everything becomes so right. Fine. What was the nice thing here?
Sir, at least one pair of its neighbors are not adjacent.
Good. So the issue is that there are 2 vertices of its neighbors. Two of its neighbors got the same color. Right? They were not adjacent, and 2 of its neighbors luckily got the same color. That is very much possible. And in that case, we are done. So if 2 of its neighbors get the same color, then we are done. But the problem happens when all its neighbors get different colors. And then what do I color V? This is the main question. Now, do you have any idea about it?
Sir,
Hmm?
if at least one pair of V's neighbors should not be adjacent, because if every pair is adjacent, then we will have a K5 in it.
No, it's not adjacent, right? That's true.
So
They're not.
then can we like pick one color, one of the two colors, color the second one with the same color and readjust the remaining graph?
Very good point. So main idea that you're trying to say is that this vertex, say you have this vertex W and maybe U. And W and U are 2 vertices that are not adjacent to each other. one gets red, one gets green. Now, there can be many colorings. There can be many colorings of G minus V, right? G minus V doesn't have necessarily have only one coloring. There are many colorings. So if I can somehow find a coloring when the color of V and W and color at U become same, then we are done, right? Then there is no issue. Correct. So somehow can I color U with red? Now, can I somehow have a valid coloring of G minus V when color of U is also red? Or color of W is also green? Now, they are not adjacent to each other, but they might have a long path, which is maybe they have a common vertex, then there are common vertex, then some common vertex, then some common vertex, and so on, which is forcing these two vertices to have different colors. Okay. Now, what can we say?
So maybe we can think of the subgraph which is drawn in the whiteboard. So inside that subgraph, all these 5 vertices together can be colored with 4 colors.
Which subgraph?
Like the one that you have drawn was a subgraph.
This one. This one.
No, the total 5 thing together, 5, 6 vertices together.
This one.
Yes.
This one. This is a small subgraph. This is a star graph, right? And it might very well be that none of them have any adjacent to each other. It's possible. So let's see. Why can't we color W green? What is stopping me from coloring W green? Can somebody say? What is stopping me from coloring W green?
If W has a neighbor which is colored by green color.
Very good. So maybe W have 1 or 2 neighbors, right? Both of them are, or some of them, at least one of them is colored green. Okay, that is possible. In that case, that's why I cannot color the W green. But in that case, why don't I color this vertices red and then this vertices green? That would have also solved the problem, right? I could have colored this vertices green, red and this vertex green. So what is stopping me from doing that?
Maybe those 2 vertices has something red.
Good. So maybe those 2 vertices have something which is colored red. But then I can ask again the same question. What's stopping me from green? Because not only because of this vertices, but something else that is stopping me. Okay. Now, if I keep on going like this, I will keep on producing a path. Okay. And this path cannot stop anywhere. If the path stops, so I have this red, green kind of a structure. Okay. And if considered at some point of time, say, oh, now there is nothing else. So I have a tree in some sense with a red on top and then a green tree or tree type structure, a layered graph. Red, then a green, then another red, then another set of green, and so on and so forth. And at some point of time, I said, oh, now all these vertices, they don't have any other neighbors of red or green. In that case, I could have just flipped again the red color and green color and converted this W to green. Okay. Hello, can you hear me?
Yes, sir.
Okay. See, this is what happens when you don't speak. I was speaking for some time, not knowing that I am audible or not.
You were not audible for some.
Yeah, I realized that from your chats. So, how much did you figure out? Hello, how much did you follow? Hello, am I audible?
Yes, sir.
Yeah.
Yes, sir.
So after that tree structure.
Sir.
Okay. So I just told that what happens if I have something like this? Okay. When there is a tree structure, I mean, and then all the neighbors are something, say orange or something. In this setting, can I do something? So if this is the case, so I have red, then green, then red, then green, and then it stops. And all other neighbors are say some other color, say orange. In that case, can I do something? Am I audible?
Switch the red and green colors.
Yes. So we can, in this case, we can switch the red and green color, right? And still it would be a valid coloring of the whole graph. And beautiful thing is that W will become Huh?
Green vertex.
Exactly. W will become green vertex. Right? Fine. So W becomes green vertex, and then we will be able to done. It will be done. So am I done with it? So am I, therefore, can I say that there is always a way of converting W to a color that is of U?
No.
Sir, if there is a cycle, there is a path from W to U with order number.
Exactly. Very good point. Yeah. So what happens if I have a graph path from W to U? Okay. So I have a path from time. If I flip the red and the green, what will happen is that W will be colored green, but U will be colored red, and it will not be that useful. Right? Hello.
Yes, sir.
Okay. But now comes the next question. In that case, what happens? Say this, call this one X and this is Z. Can I color X to Z? Can I color X with yellow or Z with green or with orange? What do you
In
think?
this graph we can. Yes, we can. Because X and if X and Z are connected, then it will not be planar.
Exactly. Oh, see, there is a path from now. I get this path, right? A cycle. X is within, Z is within. So I now do the same thing with X and Z, meaning say maybe X has a neighbor which is yellow in color, and so on and so forth. But this path cannot cross this cycle. So this path or this kind of a tree structure will always be contained within here. And in that case, I should be able to change the yellow and orange color in X in this part without affecting anything else. We can just convert the yellow and orange color here. And which will mean that I would be able to color X to yellow. So either I can therefore color W to green, or if not, I can color X to yellow. Okay. Is this fine? And in that case, I should be able to color it with Am I audible?
Sir, your voice was breaking. Now you are audible.
Okay. So,
Hello.
did you follow this argument?
Sir, can you repeat the last part?
Yeah. So the last part that I told was that so either therefore so there is this path here, right? As if W to U to V to W. Okay, and now I can do the same thing with X. There cannot be a this orange yellow path from X to Z. So the orange yellow path must be contained within this cycle, which would mean that I can replace or flip orange to yellow and yellow to orange in this space without changing anything of the rest of it, of the rest of the graph. And therefore, X will be colored yellow and Z will also remain yellow. Right? So in other words, either I can color W to green or X to yellow.
I did not get the part where there cannot be a path from X to Z.
Yes.
So why?
Can there be a path from X to Z, which is of orange and yellow? Do you think such a path is possible? Say orange and then this one. Is this path possible? Do you think is this path possible?
Yes, sir.
It is possible. But what is the thing that we have? We have a planar graph. This is a planar embedding. Hello. Now, when you are asking a question, can you please
Yes,
keep
sir.
yourself unmuted so that I can understand whether you can hear me or not? Yeah.
Yes, sir.
So since it is a planar graph, and this is the enclosed path, right? Enclosed path. X is within, Z is outside. So any path from X to Z must cut this path, right?
Okay, sir. Yes.
This whole path from X to Z is yellow and orange. So it's not like you can use a vertex from part.
Yes, sir. So it is crossing the that enclosed region, so it is not planar.
It is not a planar. So we are using the planarity here.
Okay.
So it is not cannot be there.
Yes, sir. Got it.
Okay. Okay. So this one was a very quick and kind of simple proof of the 5-color theorem. You might want to try out the 4-color theorem, but it is very hard, much more harder, let's put it this way. And in fact, there is no clean solution to it. So I don't think I will go into 4-color theorem. But this is the beauty of the inner graphs that are there over here. So do you have any questions? So I think with this I come to the end of this, whatever materials that I wanted to cover in this course. We have done, to recap the things that we have done. We have done basic logic. So things done in this course. Basic logic, propositional and predicate. Proof systems. Okay. Then we had done counting, recurrences. Yes. Counting. Generating functions. Then asymptotic notations. Then we had graphs. So we had graphs, and inside graphs, what all things have been done. Inside graphs, things that have been done are other than the basic definitions. Connectivity. Flows. Sorry. Trees and trees. Flows. Matching. I mean, in fact, it was the max cut. Planarity. And then there were certain things that were done which were not given or not actually, but were given as a exercise or something like that.
So your voice is breaking.
I think sir got disconnected.
Hello. Hello, am I audible?
Yes. Yes, sir, but your screen is not there.
Yeah, but you could see whatever I was writing there.
No, sir.
I mean, how far did you see it?
Until flows and matching.
Okay, fine. Since flows and magic, let me just say it what I was about to say after that. After that, flows and matching, we have done planarity, right? And other than that, we have done a bit of other things which have not been covered in the class, but have been given as a in the exercises and so on, like colorability, the independent set. I mean, we have not done too much stuff over that, but we know the definitions. We have used something of that, and more or less that is it. Okay. So this is what. So I will share the screen, or I will share the file with you guys. I will upload it in the web page. You will see all this list. But other than that, more or less, yeah. So this is what we have done, and so please be ready with questions from everywhere. The exam will not be very hard, particularly if you are following the class. It should not be hard. Okay. It is 100 marks question, and I will ask you guys to write it as much as neatly as possible. This is something the only request I can have. Okay, I know the usually we insist that everything is written very formally, but in this course, I mean, I'm not really going to insist too much formality here, because of this COVID situation and all, we have not been able to really go over all the formal ways of writing proofs and all those things. But please do write neatly. Ideally, one problem per paper. And the other thing that I just wanted to just tell you guys that since you guys will be coming to the campus for the exams, I don't know how much familiar are you with the ISI campus, but in the ISI campus there is a building called a PJA building. Platinum Jubilee Auditorium building, and sometimes it is also nicknamed as the dinosaur building. So there is a big fossil of dinosaur in the ground floor. So in the 6th floor of that building, my office is. If you have any questions, if you want to meet me and ask me directly, you may do so by just walking into my office. I am usually in my office from every day from say 11 to 6. Okay, so if you have any doubts, any questions, feel free to ask me. Also, can you just let me know if you guys want some tutorials? So if you don't want tutorials, there will be no more class and that's it. If you want tutorials, today at 2 o'clock, there is a possibility. If you don't want it today, there is a possibility on say Sunday or anytime next week. It will be purely on trying to solving problems, clearing doubts. Either I or some TAs will be taking it. Do you have any doubts, questions, suggestions? Please shout out. Yeah.
One question for graph.
Sorry.
Sir, for graph theory, going through the class notes is enough, or we will need to read some book?
Going through the class notes is more than enough. Going through the class notes and
Hello.
more importantly, solving the problems in the exercises and assignments. Solving
sir.
problems, the exercise and assignments is more than enough. Yeah, somebody else am I asking something? Yeah, Tanmay, are you going to ask something?
Sir, I have the same question. We go through the book or not?
You don't have to go through the book. Whatever we have done, if you did not get a concept, then you can refer to the book to understand it, or you can come back to us. But if you understand whatever we have told in class, and if you can do the problems that has been uploaded as an exercise or assignments, you should be fine.
Okay, sir.
Sir, in the class, the last example, 5 colorable problem,
Yeah.
the way you are delivering it is excellent. So I understand it properly. But if I want to write it, then it becomes very, you do it with 5 colors and all those things, there is a path. But writing it formally is very difficult.
That is true. I mean, writing this such a theorem formally will require some practice. So, okay, first of all, I am not going to ask you to prove this theorem in the class, okay, in the exam. So you don't have to worry about writing that one. And if you want to know about how to write it, so either you can look at it in some books. Any book will have a 5-color theorem and the proof of it. You will find the proof will be same, just that formal way of writing it. Or I can also upload maybe send a link to one nice write-up about 5-color theorem. Okay, I mean, there's 2 parts of it. One is understanding the proof, one is writing the proof. And with the writing the proof part we are talking about, and it is surely doable. I mean, for that thing you might want to take a look at the book or some other notes. But I mean, something so complicated as this will not be asked in the exam. So it's not something that you should be really losing your sleep out of that. Any questions? Any other questions? Nothing? Okay, if there's no other questions, then let me stop here. Please let me know if you want a tutorial or not. Anybody can ask it, okay? You don't have to ask for everybody. if you want a tutorial to have some practice problems, to discuss some problems, anytime from today to the start of the exam day, anytime you can drop me a mail or drop a mail, write a thing in the classroom saying that can we have a tutorial on this topic or something like that, and we will arrange something. But you guys have to ask it. If now no one of you ask it, there will be no tutorial. There will be no problem solving. So then I will assume that you guys are all extremely smart and have understood everything. No doubts about that.
Excuse me, sir.
Yeah.
I had a question not related to the course. Will you be speaking at the conference that is there today?
No, I will not be speaking. I will be chairing a session. Chairing a session is different from speaking. I will be conducting who will speak and all. Okay, so fine. I think if there's no other questions, let's stop now. Okay, thanks.
Thank you, sir.
Thank you.